In this video, we're going to review all of the concepts associated with power series. So I'm going to give a function, namely f of x is equal to 1 divided by x squared minus 8x plus 16. We're going to find the power series for this function, and then we're going to find its interval and radius of convergence. So we're going to begin by finding the power series for this function f. So solution. So let's begin by looking at this in another perspective. So the bottom can factor in x minus 4 times x minus 4. So you can rewrite this instead as 1 divided by x minus 4, the quantity squared. So we should recognize this function as the derivative of some other function, and then we can use that, what we call antiderivative, to sort of figure out what the power series is going to be equal to. So we're going to let capital F of x be equal to negative 1 divided by x minus 4. So we can clearly rewrite this. So we can rewrite this as plus c, of course, which is the same thing as 1 over 4 minus x plus c. So what is so special about this function? So one can verify that the derivative of capital F of x is equal to little f of x. And I'll leave this as an exercise for those that are interested. So what I'm going to do is I'm actually going to find the power series for this function, and then I'm going to relate it to the power series of the original. So what do I have here? So f of x, capital F, this is going to be equal to, so what I'm going to do is I'm going to factor out a 4 out of this bottom. So once I do that, I'm going to get 1/4 times 1 over 1 minus x divided by 4. So once I have this, I'm going to let u be equal to x over 4. So I have f of x, or f of u rather, is 1/4 times 1 over 1 minus u. So if u belongs to the interval 0, 1, then we know that this is the limit of a geometric series. So let's also put our constant c here, because this c could be technically anything in terms of our original function. So if u belongs to 0, then we know that the sum from k is equal to 0 to infinity of u to the k is equal to 1 over 1 minus u. This is our geometric series. So we're going to use these things and replace 1 over 1 minus u with that expression. So we have capital F of x is equal to 1/4 times the sum from k is equal to 0 to infinity of u to the k, and then we have this arbitrary constant c. So what is u? Well, let's look at this thing in a little bit more useful context. So this is the same thing as writing f of x is equal to 1/4 times 1 plus u squared plus u cubed plus and so on, plus some arbitrary constant c. So now I'm going to figure out, okay, what is the relationship between this function and little f function? So we already verified that the derivative of capital F is equal to little f of x. So if that is the case, then u back with our definition. So u is equal to x over 4. So f of x is going to be equal to 1/16 times, actually, we can rewrite this as 1/4 times 1 plus x over 4 plus x squared over 4 squared plus x cubed over 4 cubed plus and so on, plus c. Then little f of x is going to be the derivative of this expression. So we can rewrite this as, so the derivative of 1/4 times 1 is going to be 0. The derivative of x over 4 is going to be 1/4 plus, so the derivative of x squared is going to be 2x over 4 squared. And then we're going to have 3x squared over 4 cubed. And then what would be next in the sequence? So that's going to be 4x cubed all over 4 to the 4th, plus and so on. So what do I have here? So I can factor out a 1/4 out of this expression. So I can rewrite this as f of x is equal to 1/4 times 1 plus, let's see here. So we have 2x over 4 to the first plus 3x squared over 4 to the second plus 4x cubed over 4 to the third plus and so on. So we can sort of group our x and our 4 since they both have the same exact power. So you can rewrite this as f of x is equal to 1/4. Yes, 1/4 times. So we're going to have 1 times x over 4 to the 0 plus 2 times x over 4 to the first plus 3 times x over 4 to the second plus 4 times x over 4 to the third plus and so on. So we have that f of x is equal to 1/4, and now we can rewrite this in summation notation as the sum from k is equal to 0 to infinity. So our leading coefficient is always 1 more than the exponent, so we can rewrite that as k plus 1 times x over 4 raised to the power of k. And we can rewrite that constant 4 to the k outside. So we have f of x is equal to 1/4 times the sum from k is equal to 0 to infinity of k plus 1 over 4 to the k times x to the k. So this is our power series for a function. If you want, you can easily pull that forth back into this expression and get another representation for a power series, if this is better for you. So this can be rewritten as the sum from k is equal to 0 to infinity of k plus 1 divided by 4 to the k plus 1 times x to the k. So clearly this series is centered around a is equal to 0. So we need to find the radius of convergence from 0 to see what the interval may be. So this is what I'm going to refer to as AK. So we know that the radius of convergence is equal to the limit as k goes to infinity of AK divided by AK plus 1 its absolute value. So k starts from 0 to infinity, so k plus 1 over 4k plus 1 is going to be a positive number, so we can sort of ignore these absolute value bars. So r is going to be equal to the limit as k goes to infinity of simply ak over ak plus 1. So ak in this case is k plus 1 all over 4k plus 1. And then divided, so I'm going to multiply by the reciprocal. So that's going to be 4. So I'm going to add 1. So I'm going to have k plus 2 all over k plus 2. So I need to take the limit as k goes to infinity of this expression. So I can decompose 4 to the k plus 2 into 4 to the k plus 1 times 4. So I have r is equal to the limit as k goes to infinity of k plus 1 over k plus 2. So those are those two expressions times 4 to the k plus 1 times 4 all over 4 to the k plus 1. So I'm focusing on my exponential terms. So these 4 to the k plus 1s cancel, so I can factor out my 4. So r is going to be equal to 4 times the limit as k goes to infinity of k plus 1 over k plus 2. By L'Hopital's rule, or the rational functions theorem, you can find that this limit here converges to 1. So the radius of convergence in this case is 4. So what do we have here? So we have that f of x is equal to the sum from k is equal to 0 to infinity of k plus 1 all over 4 to the k plus 1 times x to the k. So that's my power series. It's centered around 0, so my interval of convergence is going to be of the form 0 minus r and 0 plus r, or simply minus r plus r. So now I need to test my boundary points, which in this case is minus 4 and plus 4, and see if it converges at the endpoints. So I'm going to start with the left point. So f of 4, or f of negative 4, is going to be equal to the sum from k is equal to 0 to infinity of k plus 1 all over 4 to the k plus 1 times negative 4 to the power k. So we can rewrite this as the sum from k is equal to 0 to infinity. So the negative can be withdrawn, so we have negative 1 to the k. And we have a 4 to the k divided by 4 to the k plus 1, so that's just going to be k plus 1 all over 4 to the k. So this is an alternating series, so we can use the alternating series test. This term is always positive and always decreasing. So therefore it converges by the alternating series test. So that's good. But you should also note that there is a slight misprint here, because if we actually show our work in this expression, you should see this is 4 to the k all over 4 to the k times 4. So those actually cancel, and we just have this expression. So is this really an always decreasing function? No, this is actually always increasing. So this diverges, well, it's inconclusive by the alternating series test in general. So you can find that even though it is increasing, it is possible that the alternating terms do converge, but this series actually diverges. So that means negative 4 is not going to be within the interval of convergence. And if we look at the right endpoints, namely f of 4, this is going to be equal to the sum from k is equal to 0 to infinity of k plus 1 over 4 to the k plus 1 times 4 to the k, and this is going to be an infinite series as well, because this is strictly always increasing, there's no alternating terms there. So this is going to diverge as well. So with that being said, it diverges at each of the endpoints, so that means the interval of convergence is going to be precisely negative 4 to 4, where the power series, f of x, is going to be equal to the sum from k is equal to 0 to infinity of k plus 1 all over 4 to the k plus 1 times x to the power of k. And again, the proof for convergence should have been straightforward in this video, but as always, if you have any questions, feel free to leave it in the comments. But definitely I leave as an exercise to verify via whatever methods you know that the sum from k is equal to 0 from negative 1 to the k of k plus 1 divided by 4 diverges. So that's an exercise for you. Alright, hope you enjoyed.